Okay, so hello everyone, welcome to our this week Ruggers in Efficient AI seminar talk. And today we're very glad to have the Dr. Jenny Huang from the Nvidia research to give us talk about the systematic and rapid approach to design space exploration for tensor accelerators. And Jenny is a research scientist at Nvidia, and her research focuses on emerging GPU architecture and the combination of algorithm mapping and hardware to enhance the system performance. Before Nvidia, she got her PhD in the computer science from the Berkeley. During her PhD, she has worked on algorithm hardware co-design, HLS-based design methodology, and ML ILP-assisted compiler optimization and hardware DSC techniques. So now let's welcome Jenny to give us this talk.
Thank you for the introduction, Professor. Yeah. And good morning, everyone. So it's a great honor for me to be here and share our work on how to systematically and rapidly explore the design space for Tensor or AI accelerators. So I'll be discussing the challenges, the methods we developed, and show some results. Basically, I'll start with like a typical scenario a computer architect likes to face every day. So imagine you're the lead designers that are given the opportunity to architect the next generation AI accelerator for a new tensor algorithms called GPTX. So you're presented with this chip area of 800 square millimeter and the best available DRAM from the vendors. So you're free to fill this chip with either compute resources or on-chip buffers to optimize for performance. And now you'll be facing a very key design challenge, which is how do you provision the chip area among different components? So there will be storage components, compute components, and what I'm not listing here is some communication components. Also, there is some dark area for like thermal optimization. And a straightforward solution would be that we should perform a design space exploration. Assuming we have a simulator or emulator or even like existing implementation to allow us to evaluate different design options. We can basically define our architecture design space. And together with that, we also need to consider a huge mapping space so that we can fully leverage the benefits this new different architecture design can give us. But if you look at the size of this typical architecture design space we use for like Simba or like spatial accelerator design for ML, it's very big. Especially considering that we're not only changing the architecture space, we also need to find the best mapping to fully map this workload to exploit this different hardware capabilities, right? And for different simulators or evaluation tools, the evaluation time can also take pretty long, ranging from a few milliseconds to hours if you want to get a more detailed feedback for each design point. So putting all these together, we're seeing that it could potentially take trillions of years to explore all these design options, logical time, not just the real time. Yeah. So as a result, like this process can be very time consuming and costly. And a natural kind of follow-up research questions I had when I was doing my PhD is how to tackle this vast design space and get to the optimal design quickly. So the first technique I'm going to present here is called the COSA. This one is specifically trying to tackle the question on how do we efficiently map a workload on a new like spatial accelerator architecture. And it is a constraint optimization-based method we introduce to find performance and energy efficient schedules in one shot. So the following will be the slides for COSA, and this work is done in collaboration with professors from UC Berkeley, so including my advisor John, Sophia, and Jim Demo professor. So as I shown in the previous slides, there is like ever-growing complexities in the algorithm side and hardware side, and they together kind of pose a intractable search space for the schedulers. And scheduling is not only hard, but it's also very important because it can significantly impact the performance. And shown in this slide is the stacks of 40K mappings from a ConfNet, and we're trying to map it to a 4x4 NOC accelerator. We can see that from the simulator, the best and the worst schedules can differ by 7.2 times in latency, which is quite significant. And this slide lists this prior state-of-the-art work to tackle this hard and important problem. And we categorize them into 3 approaches. So the first group is like a more brute force search approach that aims to just search the space with some heuristic. And the second approach is a more feedback or data-driven approach. So they employ ML algorithm to navigate this space. And the last category is more for the constraint optimization side, that trying to formulate compiler decisions into mathematical optimizations and use standard solvers to solve them. Or not even just standard solvers, some of them will be what's it called, the ISL, right? So some of the ISL work will also just help to solve like some of the polyhedral problems. And among these approaches, the brute force and feedback-driven approaches are kind of expensive since they require many samples to work efficiently. In addition, they often samples from invalid scheduling space, since the boundary among valid and the invalid mappings cannot be straightforwardly drawn from a map space perspective. It's very hard to define such space and hard-coded the rules for valid schedule. And lastly, they typically require a new search for a new algorithm or a new hardware feature. And on the other hand, the well-known polyhedral-like frameworks, they do not handle or do not directly solve for a critical scheduling decisions, such as the tiling factor sizes. Any question? Okay. Yeah, please feel free to chime in if you have any comments. And different from all of them, so what we're trying to do in COSA is that we're trying to introduce a one-shot constraint-based optimization to deterministically solve for a good schedule, which determines the tiling factor with in one shot, basically. And we hope that it can generalize to new Tensor algorithms and ML accelerator configurations. So the idea of this work is derived from a few key insights from the domain-specific workload and accelerator designs. So the first insight is that the key components of major deep learning workload is very regular. They are dense matrix multiplication operations, and they should be statically analyzable. And the second insight we leverage here is that like the hardware is not a black box either. We could also leverage the easily obtained hardware constraint to help us prune this scheduling space. And lastly, unlike the general purpose processors, many DNN accelerators require explicit data management. Basically, however, so basically we would know where the Tensor stores in different buffer level. So unlike in the cache, that's basically implicitly managed by the hardware itself. And so however, but existing hardware always kind of treat them as like a black box, and kind of just based on the feedback and trying to generate a high performance schedule based on only the feedback, not kind of considering any of these informations from the ML algorithms or the ML hardware. So with these insights in mind, we will now introduce our own methodology. So I'll start with the target workload specification. So again, we are trying to target dense matrix operations, such as convolution and matrix multiplication, or even like BMMs if you're doing like a large language model kind of research. So these kind of computation can be, so if I take convolution as an example, they can be defined with a few rank dimensions. So in this example for convolution, we have RS, PQ, CKN. So each represents a different shape or dimensions of the workflow. So RS is the filter width and height, PQ are the output width and height, C is the input channel size, K is the output channel size, and N is the batch size for convolution. And the computation of the convolution can just be implemented with the 7 nested loops as shown on the right-hand side. And COSA kind of targets the accelerator architecture with spatially laid out PE and a multi-level memory hierarchy. So this hardware constraints we show in this example are basically within each PE, we will have 64 MAC, and we assume that we have 8x8 number of registers, and each of them is gonna have entry size of 1. And the outer loop, we have an accumulator buffer, which has 128 entries, and together with a size of 384 bytes. And outside of accumulator relation buffer, we will have a weight buffer and input buffer to kind of store the weight tensor and input tensor separately. And basically, this is a typical design we borrowed, or like we directly used the constraint from the Simba chip. Also, it was a research project from Nvidia that they tape out a multi-chip module, and they designed this ML accelerator basically to study whether there are any benefits to shift from single chip to multi-chip module. So given this DNN layer dimensions I mentioned and the target accelerator specification, our scheduling framework called COSA trying to formulate this scheduling problem into a standard integer linear program. Oh, it's not linear, sorry, integer programming problem with basically you have to define your variables, constraints, and objectives. So the expected output of the schedule is a decision on basically how we kind of organize we lower the workload and organize it in a for loops, right? So there are 3 key decisions to be made. First one is the tiling factor, which is the loop bound of each tiled loop, that can affect the buffer utilization and the overall traffic to different level of memory hierarchy. And next, we will have the spatial and temporal decision to make to indicate whether a loop tile should be mapped for spatial or temporal execution. And lastly, we have loop permutation to specify the ordering of different ranks in each level of the loop nest, which will affect the overall data flow and the reuse pattern, and consequently affect the overall traffic. And the key idea of COSA is to kind of turn this scheduling problem into a prime factor allocation problem of the ranks and solve for the allocation variables. So here is a simple example we use to demonstrate how COSA works. So given a matrix vector workflow as shown in the for loops on the left-hand side, it has a input vector size of 28 and an output vector size of 15. And we have 2 levels of buffers to schedule into. One is the weight buffer, the other is the global buffer. So we need to break this loop bounds or the rank size into the prime factors. So we have 28 kind of gets split into 2 to 7 for the prime factors, and 15 gets split into 3 and 5. And we can now treat each buffer as a box with limited capacity that we can put these prime factors into. And here is one kind of example variable allocation to tile this 2 rank into the 2 buffers in the memory. So basically we put 2 to the weight buffer and 3 to the global buffer. And there are some other like according like Yeah, so the rest of them are kind of allocated to the DRAM. So we're not putting them in this slides. And based on this specification, we now can actually calculate the buffer occupancy based on this binary variable, right? So for the weight buffer size, we have an allocation of just 2 factors. And for the global buffers, basically we need to kind of take into account of all the factors that's been put in the weight buffer and the global buffer, which includes the weight tensor as well. It's kind of inclusive memory hierarchy. Then the utilized capacity of this buffer will be 2 by 2 by 3. Basically, all the prime factor has been allocated to the weight buffer and the global buffer. And likewise, for each memory buffer level, we need to kind of assign whether a prime factor that's allocated to this current level will be specified as a spatial factor or a temporal factor, right? So in this case, assuming we only have 4 of this weight buffer, then we basically can only assign a vector of size which was multiple size is smaller than 4 to the spatial part. And the last decision we need to make is basically the permutation. So for permutation, we also kind of design a way to allocate the prime factors in 2 different ranks. Basically, the idea is that if a prime factor is assigned to rank 0, for example, the 2 is assigned to rank 0, it will be put in the innermost loop of the level. And likewise, basically based on the rank order, it will be allocated or will be lower to the same loop ordering at each level of this memory hierarchy. So as a result, by specifying this variable x with the memory level allocation, the spatial temporal decision, whether it's spatial or temporal, it will be specified, and also which rank each factor should be assigned to. We basically could translate that directly into a valid mappings, or not a valid, but translated to a mapping options in COSA. And in addition to the variables, we next we need to figure out is how do we constrain this problem. So we will always only search for the valid mappings in the space. So the first constraint we consider is the buffer utilization, as I mentioned before. So we kind of need to make sure that our allocated prime factors product wouldn't be larger than the buffer's capacity in this case. And for example, for the last example, if we have like a factor that's larger than the buffer size, then it will be considered as invalid mapping by the solver itself. So we only need to explicitly express this constraint so that the solver can kind of filter out these invalid mappings. And the next constraint will be for the spatial resources. It's applied the same way as the utilization constraints. And trick, basically now you'll be wondering that right now we're kind of, for every decision, we're kind of multiplying all the variables together, right? So that sounds like a nonlinear problem that cannot be directly solved by the typical like integer programming tool. But there's a trick we applied here to kind of turn these product terms into linear sums of log prime factors. So here's how we kind of perform this trick. So the idea here is that if we specify a variable x3, meaning that if we put the factor 3 at memory level 0, or if we put the factor 2 at memory level 1. So this if statement, so if this variable is 1, then in our program, we will need to multiply this capacity kind of calculation with 3. And if the variable is 2, then 2, 0 is 1, we'll need to multiply by 2, but otherwise we will not multiply it with any extra factors, right? So in this case, what we did is we actually can take the log of each of the term so that we can turn this into a linear formula. Basically, in this case, you can see that if we turn both sides into a log equation, it will become linear programming formulation, because when the x variable is 1, we're basically multiplying the log factor of 3. Sorry, we're multiplying with the log. So the log factor will be multiplied with 1 if the variable is 1, and the log factor will be multiplied with 0 if the binary variable is 0. But then if we turn it back into the non-log term, basically this is equivalent to multiply this value by 3 or multiply it by 1, right? So that's how we kind of formulate this problem into a integer, linear, or even a quadratic programming problem that could be directly solved by the solver. So this is a very useful trick, I would say, in optimizing for this problem. And with that, we kind of need to start to define our objectives. So the first objective is kind of, as we defined before, is just trying to just maximize the utilization of all buffers, so we can lower the communication cost. So basically, we can use the same buffer utilization formulation as constraints as we use the buffer utilization constraints as the objective, basically, in this case. And the second objective we use in this work is trying to minimize the compute cycles by maximizing the factors that are mapped for temporal execution. So by minimizing the factor for temporal execution and maximize the factor for spatial execution, so that we have more elements to run in parallel to shorten the compute time. And lastly is the most tricky one to define, which is the traffic to the next outer level as an objective. So here, actually, we introduce a nonlinear term here. So we make this problem a little quadratic to define these traffic-driven objectives. And if you think about how a loop traffic is defined, right? So first, we will need to consider the tile size that, so for each tensor, starting from the innermost buffer level, we will need to kind of first define the tile size for each traffic. So in that case, whatever tile that's within my current buffer level that's relevant to a tensor, I will use it for the calculation of the traffic size. And the next thing we will need to consider is whether this traffic is being unicast on the multicast. So if my rank, basically if it's k, it's relevant to my weight, that means this traffic is unicast because we're sending a separate items of the weight array to each of the weight buffer. But if it's, let's say this dimension is a p dimension, which is a relevant rank to the weight, then this traffic will be multicast, meaning that the traffic will be loaded once from the backing store and being sent multiple times, like send the copies. The copies will be sent to different weight buffer in different PEs in this design. And the last thing we need to multiply this over traffic by will be the temporal iterations of how many times this tensor need to be sent from the backing store. And the way we determine it is we kind of introduce another binary variable to indicate which rank basically we're seeing irrelevant dimensions. So the way we determine the outer loop iteration is that starting from the innermost loop that's outside of my current buffer, right? I need to take a look and see whether this rank is relevant to my tensor. So assuming C is relevant to my weight tensor, that means starting from this level, every level outside of this, I need to multiply the traffic by that number, by the tiles factor, because every time the C changes, so I'm loading a new weight. So the level which you are seeing the first relevant rank to the tensor of interest kind of determines how much traffic we are seeing for the overall calculation. And so a typical way when people think about it is they kind of define it as weight stationary, output stationary, and input stationary. So what it says basically is that like if we have an irrelevant rank for weight stationary at the innermost ones, we're basically reusing the weights for the innermost rank times, right? So that's how we calculate this overall traffic and kind of reason about different data flow using this traffic-driven objective. And here comes our evaluation. So this is done like a few years ago. So we're using a very old set of conv network benchmarks. So we are using a simulator called Time Loop, also is developed at Nvidia as an analytical model to kind of show the energy and latency performance of a analytically defined hardware accelerator. So with this, we can show that when we compare COSA to hybrid search or random search, we can find a better design, that better mappings that lead to 1.5 times latency speed up compared to other methods. And we can see that we also can find a better energy, if better mappings with higher energy efficiency compared to the existing methods. And what's more is that the time to solution with COSA is much faster compared to a search-based algorithms such as random search or hybrid search. So we also kind of compare for different architecture setup with like larger buffers for the global buffers and more PEs. We're seeing different speed up number for these different configurations compared to the baseline search algorithms. And if we're doing like a rough search over the like TVM-based ML kind of driven solutions, we are running much faster because it takes so much shorter time to run this formulation with Gurobi. And we're still also seeing some performance speed up on the GPUs compared to the TVM searched output. But I think one thing I want to mention for this one is that like in GPU, there are a lot of like non-deterministic behaviors. So sometimes fine tuning is due demand because we really don't know like the basically the SMs, for example, they are having very dynamic behaviors based on, let's say, the power or even just temperature of where this SM locates. So sometimes in order to achieve the best performance, fine tuning is still required for this implicitly managed systems like GPUs. And likewise, for example, there are some L2 and latency and stuff that COSA is not considering in its formulation. So in that case, sometimes fine tuning could be still a very important kind of technique in order to get us to the last bit of the performance here. And so with that, we kind of think that we were able to kind of tackle this mapping space in one shot and quickly generate high performance and energy efficient schedules. And next, I'm going to talk about our work to kind of trying to reduce another space in the design space exploration, which is just the architecture design space. And at this time, we will kind of trying to use another technique, which is ML-based technique to try to transform the architecture design space and make it more friendly for the search algorithms to navigate. So this is, again, the work I've done at Berkeley and together with my advisor and Sophia. So here are some challenges in this space to efficiently navigate the architecture design choices. So first, this design space is both very high dimensional and discrete. So if we consider a open source accelerator, again, this is the Simba accelerator for deep learning, developed at Nvidia. Its design space would include parameters like the number of processing units and number of mag units and various buffer sizes. So all of which kind of contribute to this high dimensional configuration space. And each of these parameters can take a range of kind of discrete values. So for example, there's also some network specification saying that whether it's a mesh network or torrents, they're more kind of discrete than this only value-based discrete configurations. And what's more is that like this discreteness is kind of further amplified by the mapping options. So with some of the mappings are invalid only so within certain buffer capacities. So it can become invalid even with this kind of sort of like integer kind of continuous values, right? But then in the performance in the performance evaluation, what we're seeing is that like even though the value here could be continuous in integer domain, it's still not continuous in the objective domain because of the mapping, because sometimes the mapping could be invalid if it exceeds the buffer capacity, right? And where it can exceed this capacity would be a problem of the mapping. And the second challenge we're facing in this domain is that like we typically will use more than one metric to evaluate the hardware design. So for instance, latency and energies are the two objectives the designers commonly target at the same time. So optimizing them separately wouldn't give us the optimal things that we want. And as we can see from the two plots from the ResNet, basically if we trying to optimize the latency, we could potentially lead to an increase in energy, and the search space becomes non-trivial for finding this Pareto optimal points. In addition, like these points, as you can see from this figure for the energy specifically, they are non-convex, which makes it very hard for existing algorithm to perform. And here are some prior work for tackling the hardware design space exploration. So ranging from the heuristic-driven approaches guided by the designer's intuition, which is interstellar, we list here, and to black box optimizations with like Bayesian optimization or evolutionary algorithms that leverages like basically basic typical ML algorithms in optimizing I would say like unknown kind of objectives, and you kind of build up. So for the Bayesian optimization, you kind of build up an internal continuous model as you kind of sample. With evolutionary algorithms, it's more like a greedy approach to kind of sample for the promising candidates. You just sample from the best pool, and then you kind of spawn from that pool to kind of evolve and trying to find better solutions. And lastly, we have also the gradient-based optimization, which kind of requires us to kind of train a model and perform the search on this model. So each of this kind of strategy has its pros and cons. But one common things that shares among them is that they only performs either the search or the heuristic on this original design space. And this technique trying to basically efficiently navigate this in this original kind of search space. But as we learned before, like certain nature of this original space will make it kind of challenging for search algorithms that requires low dimensionality, such as the Bayesian optimization, and smoothness of this design space to such as the gradient descent to perform. So our thought was that can we generate a new search space, one that is more friendly for existing search algorithms to search on, basically. So ideally, what we want is that we want to have a space that is with reduced dimensionality, so we can analyze and navigate this search space more easily. And second, we want to perform, so we want this, when we do like gradient descent like algorithms, we want this performance or the objective space to be a little bit smoother, so that the gradient-based like solutions can work more effectively without getting trapped into like local optimals. And last, we kind of need to reconstruct this space to the original space so that we can map the optimal designs we found in this or a new latent space back to the original space for evaluation. So now we have kind of identified the desirable properties of this new design space. The question will be how will we achieve this, right? And we learned that there is a machine learning algorithm that can help us solve all these challenges and provide the properties that we want, as mentioned above. And it is the variational autoencoder. So here's like a detailed introduction of what VAE is. So it is a it's a feed-forward model that predicts the output prime from input X through a bottleneck layer with reduced dimensions. So the training of the encoder and decoder network, trying to minimize the mean square errors between this input X and output prime. So as a layer Z, the bottleneck layer Z, after training, it will become a lower dimensional representation of the input variable X or the input feature X. Because we're able to recover this information from the Z vector back to the X prime that resembles the input X. And what makes this model variational is that the encoder network predicts a mean and a standard deviation for a normal distribution, and the latent point is drawn from the distribution. So this way, more points in the latent space can be corresponding to one original point in the original space. A popular kind of application for VAE in the past was image synthesis, right? So since you can learn the underlying latent features by identifying the structure in the data, it kind of can provide us a low dimensional feature space that we can understand and tune so that we can modify an image, for example, a human face based on different features in the latent space. And we can tweak different features here to kind of reconstruct a face with features we like. Another applications for like chemical design, it's also from a pretty early work in 2018. Basically, you can reconstruct, you can use VAE to explore new chemical designs. Basically, you can kind of learn this latent space, and based on the region you're interested in kind of modifying this chemical like designs and molecule designs in, you can kind of tune its property to generate new like molecule designs that you're interested in with the features you want. So our work is pretty much inspired by this work, right? It's kind of likewise. We always want to take a design and modify it in a space towards a better performance, basically some feature we want, and we want to generate the corresponding configuration for it. So so here we introduce our work called VISA, which is VAE for Spatial Accelerator Design, to introduce this new kind of design space for hardware design. So just like this VAE pipeline we showed previously, the VISA provides a transformed search space for hardware design space exploration through this encoder. And then once we train this latent space, we perform search on this latent space and find a performance point. And we decode this performance point to the original hardware design space for evaluation. And now you might wonder how we train this pipeline, right? So let's take a deeper dive into the training process. So here's the diagram that demonstrates the training process. So we start with gathering a data set of hardware configuration and the corresponding latency and energy labels, running different DNN layers. Then we feed the hardware configurations as input data through the encoder to the encoder and produce the corresponding latent representations. Sorry. And along with the VAE, we kind of introduce this latency and energy predictors, which takes the latent space features and DNN configurations as input and estimate the energy and the latency. So we take this latent space features representation of the hardware and the layer configuration as input for the predictor to predict the energy and the latency. We then pass this latent representation of the input configuration through the decoder to predict the output hardware configuration. We then gather the input hardware configuration as the label for the output of the VAEs and gather this actual latency and energy as labels for the performance prediction from the latent space. And the loss function of the VAE is defined as the difference between the inputs and the input hardware configurations and the output hardware configurations of VAE, plus some regulation terms, which we'll discuss later. And the loss function of the predictor is defined as the difference between the actual and the predicted hardware performance. So when we do the training, we're trying to minimize both of the loss at the same time through backpropagation. And the reason we're trying to train this predictor along the VAE is that we wanted to provide a more performance information for the VAE to structure this latent design space. So it will hopefully it will kind of categorize different performance region, like it will have different regions for different kind of performance behaviors. And here is like a visualization of the trained latent space. So we took this 2D latent space example we trained in VISA and visualize it. So the color represents the magnitude of various properties of the hardware design. And so the first kind of two figures shows how the design with different number of MAC units and global buffer sizes are arranged in this 2D latent space. And the last figure shows how this design with different EDPs are organized in this 2D space. We can see kind of like good clustering and structure in this plot. And the last figure specifically showed that by adding the predictor in the VAE pipeline, we can rearrange the designs in the latent space such that the points with similar energy delay product will get closer to each other. And we also kind of visualize the latent space to understand how different hyperparameters change affect the VAE training. So I'll skip that. And we also kind of try to study what dimensionality is reasonable. So we cannot reduce it all the way to 1 as it will introduce very high loss, but it seems if we train for a long enough time, maybe a latent space of 4 is reasonable in this design. And here's the visualization of the latent space latency and as compared to the latency we get from a decoded accelerator. Likewise for the energy. And next I'm going to talk about how we run inference over this latent space to obtain better design points through Bayesian optimization and gradient descent. So here's the inference pipeline. So I'll skip that. Basically, we will just sample in the latent space using black box optimization or a gray box optimization gradient descent, right? And so I will skip what, I assume you know what the Bayesian optimization is. So with that, we're showing that with Bayesian optimization and on the VAE compared to Bayesian optimization on the original space, if we perform the Bayesian optimization on this latent space, it will converge much faster than the original Bayesian optimization, and it will actually basically it will also outperform random. So the actual Bayesian optimization on the original space, it does not outperform random, as it kind of created some bias with not enough sampling if we're just only using Bayesian optimization. And we're also showing that we can also outperform gradient descent in this case. Let me skip this as well. So I think you're all very familiar with the gradient descent, but we're just trying to perform a gradient descent over the latent space because we're assuming it's a more continuous and smooth surface. So it's beneficial for the gradient descent to kind of gets down to the optimal design points easily. And likewise, we're showing that if we're performing gradient descent on the VAE space, it's gonna be way more sample efficient than if we're performing the search on the original space. So with that, we kind of demonstrate that we can construct a manageable latent space for architecture design using machine learning and how it can be used to improve the search space efficiency. And so now it seems that we have successfully addressed the design space exploration challenge with the techniques we discussed before. However, what we really learn from these searches, right? So without an exhaustive search, we still don't know if the resulting designs are truly the optimal. Or the question would be, how far are they from the best possible solution for the ML design, right? ML accelerator design. And moreover, so every time we kind of need to have a new algorithm features or there's a new technologies in the hardware, and if we want to optimize for additional metrics, saying the power, we kind of need to redevelop this new simulator. Basically, we need to have a feedback in order to perform the design space exploration, and we kind of need to spend time and implement features and redo the whole search again. So which could kind of potentially lead to very long development cycles just to assess the benefit of different hardware features. So as an alternative in the real world, architects often kind of just turn to a roofline analysis with kind of speeds and feeds calculation to develop a very fast design intuition in early stage design space exploration. And this analysis is typically carried out using what we call this algorithmic maximum operational intensity, which is the total compute of an algorithm divided by the algorithm minimum data access count, and which will be equivalent to the sum of all the operand size in a tensor algorithm. So, and by looking up this roofline performance model with this operational intensity, we can decide whether to add more compute resources or just simply increase the memory bandwidth to further improve the performance. So this kind of gives us like a first pass kind of decisions on whether we need more bandwidth or more compute. Wait a second, there's really no consideration of the trade-off between the storage and compute capacity in this analysis. So now it seems that we actually don't have a good tool in the early stage of design space exploration to help us quickly identify this optimal buffer to compute ratio on chip, which is basically a key design question for this ML accelerators. And if we take a step back and think about what is missing from this simple roofline-based analysis, so it might have already occurred to you that the real workload implementation rarely operates with algorithm minimum data movement or the optimal operational intensity. And we're seeing a gap between the algorithm minimum data movement and the actual attainable data movement. And this is what our work called Mind the Gap that's published in last year's ISCA is trying to tackle. So this is a work at Nvidia, and we basically done with my collaborators, Nvidia and MIT, with Joe and Anshu. And here is an example showing that why there's such a gap. So basically, we're showing with a real workload running on A100. Basically, you can see that the actual backing store access at different memory levels for matrix multiplication, they're all larger. They're much larger than the algorithm minimum data movement counts. compared to the algorithmic minimum. And this discrepancy arises because the actual backing store access or the operation intensity would depend on the mapping and the buffer size, as we shown in the previous studies, right? So how to determine this buffer size matters a lot for the minimum achievable DRAM access count or the backing store access count. So in order to look at the impact of mapping and the buffer sizes, so it would be nice if we can have a diagram looking like the one on the slide for each target tensor workload. So in this diagram for a GEM workload, the x-axis is the buffer size, and the y-axis is the amount of traffic to the backing store that is achievable with any mappings or schedules. So if you know about the MIST curve in the cache kind of studies, this is not really a MIST curve because it's not derived from a single mapping implementation. It's not from a single software's implementation and exercising different cache sizes, but it's from many Pareto optimal mappings. And we refer to this curve as the ski slope diagram, as we kind of see that the data movement always monotonically decreases with the buffer size increase. And with this kind of diagram, we are able to answer a few very important architectural design questions for a tensor algorithm. So the first question is that given a buffer capacity, what is the minimum attainable data movement count to the backing store? So as demonstrated by the gap 0 in the slides, it could be orders of magnitude away from this algorithm minimum. And the second question we have for an architecture designer is that how much buffer capacity is required to achieve the algorithm minimum backing store access count? Or equivalently, the question is how do we size the buffer so we can fully exploit or reuse opportunity from an algorithm? And as we've shown with gap 1, we don't really need to buffer all the operands in order to minimize the backing store access. And this diagram will tell you how big of a buffer do you need. And the final questions will concern how the workload benefits from the incremental increase in the buffer capacity, which can be addressed by examining the rate of change on this ski slope diagram. And now I hope that you can see why we're kind of trying to develop this ski slope curve so we can kind of get valuable insights from the workload itself and the relationship of the workload's buffer size requirement and the corresponding backing store access demand. And this brings us to our contribution in this work, which is an approach to determine these ski slope diagrams. So we call this approach our genesis, which stands for mountain creation. However, there are a few challenges in creating this ski slope diagram. So first, that we need a very tractable mapping space. And the second one is that we don't want to search the mappings for every buffer size, which can introduce a huge mapping space that we mentioned in the previous design space exploration study, right? So to address the first challenge, we kind of trying to just use a simplified two-level design. And the simplicity leads to a small map space, which allowed us to perform exhaustive search, basically. And we're also leveraging the fact that the access among any two levels of the memory hierarchy in the architecture is fractal, meaning that it doesn't matter if this is the backing store from L2 to L1, sorry, L1 to L2 or L2 to the DRAM, right? So as long as we know the bag of bytes of this memory hierarchy level, we kind of know that what will be the attainable backing store access to the next level. Oh, sorry. Yeah. And basically, here's our methodology to avoid searching the whole mapping space for every possible buffer capacity. And basically, in this case, we're given a tensor workload defined in the Einstein notation. We will perform an exhaustive search on this two-level simple architecture we call the snowcat with unconstrained buffer size. And for each of the mapping, we gather the data access counts and use the buffer utilization as the corresponding buffer capacity requirements. And the schizo diagram is basically the Pareto optimal frontier of all these mapping points. And once we derive the data movement bounds showing the schizo diagram, we can simply take its inverse and multiply it by the total compute of the algorithm to obtain the operational intensity, which is a value or it's a feature that, not a feature, but the number that the architect always use to kind of understand the nature of the algorithms, right? And if we take a look at some examples, we do for 3 different gem kernels with different shapes on this slide. So each of them is with different shapes, basically with different dimensions. And here are the data movement and the operational intensity bounds we were obtained from our genesis for these 3 gems of different shapes. So on the first figure, we can see that different shapes of gems will result in different slopes in the ski slope diagram. So we might have like a bunny hill green for the gems with the smallest weight tensor size, and we have an intermediate blue Terran curve for the medium size gem. And we have a very steep black slope for the largest gem, basically. And we also observed that there's a power law decrease in all these bounds. And if we examine this operational intensity bounds on the right-hand side carefully, we find a very interesting observation, which is that in order to fully reuse the data in the buffer, the maximum effectual buffer size to achieve this minimum data movement for a gem is approximately its smallest operand size. So in this case, if I give you a gem so now I would just ask you what is basically the buffer size required in order to achieve the minimum data access to the backing store, then the answer, you can answer it very easily with just calculating the smallest tensor involved in this gem. So this is what this kind of analysis can give us. So this is kind of like one crisp insight that we were able to derive directly from just looking at these curves. And our genesis kind of provide us a way to directly derive these curves from a very simple runs of different mappings among the Snowcat architecture. And another use of this is actually, we're not just showing a bound. At the same time, we're also showing the best data flow with our exploration of all the mappings. So as we shown on this slides, which in where different colors of the background represents the best data flow for different mappings under different buffer capacities, right? So in this case, we can see that for the gem of interest, when our buffer size is smaller than 0.5 megabytes, what this curve suggests is that, if you're a scheduling optimizer, you're writing a kernel, what you should do is you probably should consider an output stationary like data flow for your current level of buffer. And once your buffer size, if your buffer size is larger than 0.5 megabytes, the wait stationary data flow will be the better choice. So this kind of gives us additional insights into this optimal data flow subject to different buffer capacities. And this is generalizable to the gems of different, so for each gem, we'll have one different ski slope diagram, but this ski slope diagram will be generalizable across different hardware architectures. So basically, in this case, the kernel optimizers can easily kind of refer to this kind of diagram to figure out, what is the best strategy I should consider in my search if I'm trying to fine tune a schedule, right? So that's another way to use this Genesis bound output. So with this, we kind of showed that our Genesis can produce bounds that reveal very powerful design insights. And besides a single tensor operations, what we're trying to also make our Genesis do is to understand fusion. So assuming we're taking a chain of einsums or a chain of tensor operations, fusion is an effective technique to minimize this data movement further. It imposes, however, in addition to like interlayer data movement reduction, it also kind of imposes extra interlayer mapping constraints, right? Because some of the mappings in the producer layer might not lead to a valid mappings in a consumer. Basically, the consumer were not able to consume certain output from certain producer mappings. Oh, sorry. And the questions we're trying to answer here is that like, whether fusion is a good optimization to apply given the buffer capacity. And the second one is how much buffer do we need in order to benefit from operation fusion? And with this analysis for fusion in orgenesis, so basically in this example, we're trying to show that we're fusing a chain of 6 operand in the GPT 6.7 block. And with this bound, we are able to answer, basically compare the no fusion with like the fusion bound that we exploit in orgenesis. We can kind of answer this question. Basically, we can see that the fusion is non-beneficial until we are having a buffer size that's larger than tens of megabytes, right? So that means that when our buffer size is smaller than that, maybe fusion for this chain of 6 operation is not going to be beneficial. And the next question is, how much buffer do we really need to benefit from this fusion? And this curve also tells you that once you reach 320 megabytes, now you're able to fully exploit data movement reduction you can get from fusion. So this is the insights that we're trying to obtain with this design methodology. And so as we shown in the results above that, the analysis kind of demonstrate that the capability of orgenesis can basically in comprehending these complex workloads, such as the workload with fusion. And now we can understand how the buffer size impacts the data movement and operation intensity. We can now use it to really help us provision the chip area between the storage and compute. And here's the way of doing it. So first, if we look up the attainable operational intensity from our operational intensity bound diagram using the buffer size as input, we can gather this achievable operational intensity number. And then now we plug in the operational intensity output to the well-known REFAI model to roughly estimate the throughput performance. So we now can directly if we combine these two models together, we can now craft this final performance bound with only the buffer size as input and the peak throughput performance as output. So we are eliminating the variable or the unknown operational intensity bound, which is dependent on the implementation. So now the REFAI model we have, it's only based on the hardware properties, which is the buffer size and the bandwidth, right? So this can give us a performance estimation of different tensor algorithms. So with this, we can kind of build a buffer-based performance bound. And by using this bound and the chip hardware specification, we can then construct a performance model as a function of the buffer area ratio, assuming unlimited compute resources on this, as shown on the slides. So we can see that the performance increases as the buffer size increase because a larger buffer will further facilitate data movement reduction. And likewise, if assuming we are only limited by the compute resources, we can construct a compute limited performance bound as shown on this slide, which decreases linearly with the buffer area ratio increase. And by combining the two curves, we can produce a kind of mountain-like performance bound to with respect to the buffer area ratio. And when the buffer area ratio is small, the workload performance we can see is limited by the memory bandwidth due to the high volume of data movement. And when the buffer gets bigger, it starts to be bounded by the compute resources as we are sizing them complementarily, right? So since this curve is concave, we can kind of very quickly pinpoint the optimal buffer area ratio for the design. So once we have this concave performance model with respect to the buffer area ratio, now we can use it to answer our initial question, which is how do we provision among the storage and the compute? And now we can just directly solve this problem at a very early stage of design space without building any simulators, right? But this provides us like a optimal bound on how much benefit we can get with this optimal analytical performance, right? So everything is analytical, but then it provides a very valuable lessons we can learn from these bounds. And once we have committed to building of like simulators or implementations, we can always refer back to this bound to see, oh, how much margin we're still having in designing these accelerators. And this kind of demonstrates our last contribution for this work, which is that it complements this roofline analytical model to kind of also provide this buffer size suggestions at a very early stage of design space exploration. So to conclude, this is a very radically design approach for early stage architecture design space exploration. It offers visualizations and insights for design trade-offs and will be a very powerful add-on to the roofline performance model for very fast speeds and feeds analysis. So this concludes my talk for today. Sorry, I ran a little bit over time. And to quickly recap, we discussed the 3 approaches for tackling the design space exploration. So COSA, which is a one-shot constraint optimization-based scheduler to reduce the mapping search time. We then look at the VISA to kind of see whether it's possible to construct a continuous and reconstructible latent space to facilitate the hardware's design space search. And lastly, we introduced a bound-driven design methodology that helps to derive transferable and generalizable early-stage design insights to help us make better design decisions without committing a very expensive search. And so if you're interested in any of this work, I encourage you to dive deeper into the papers, and please feel free to reach out to me if you're interested and have any questions and want to explore any further collaboration opportunities. And we're looking for interns next summer. So thanks again for attending this talk, and I hope you find it helpful. Yeah.
Yeah, thank you, Jenny. So this is a very complete presentation to cover all the very important design factors for the design space exploration. So I think we already have some the questions in the chat box. Can you see that?
Oh, I do not see them. 1 second. Should I? Yes. So the first question is, can I understand your second work VAE like this way? Use some data to get a well-trained VAE network and sample latent space to explore a much wider design space. So this is a very good question. So yes, if we have enough data to construct this latent space, we think that if we are exploring the latent space, it will help you explore this wider and more performant hardware space faster. So that's the goal of this latent space. So how don't have I answered your question? So I think that the answer is yes, we wanted to use it to explore more wider design space, but then I want to mention here is that like there's always a balance among the exploitation and exploration. if we have gathered good enough data to construct the latent space, if it's really comprehensive set of data to construct this latent space, then I think that latent space is transferable, so it can facilitate our exploration for wider design space. But then if our training data is not comprehensive enough, it's possible that it also present a prior into your latent space, so that it will also kind of prevent you from exploring a better, wider hardware design space if basically it hasn't seen the region with better performance, then it might not encourage the search to go to that direction, right? So there's always a trade-off among the exploration and the exploitation in this construction, yeah. But I will really I think the key problem for most of the ML-driven approach to enable transferability or generalizability is really through data collection. So if you have wide enough data distribution, I think that could solve the problem. But the harder part is on the data collection. And the second question from Hai Liang is that for the VAE performance energy prediction, does it take mapping space into consideration? Yes, that's a good question. And you already kind of found the answer. We actually use COSA to directly generate the high performance mapping to basically tackle this mapping space problem. So we use COSA to directly generate high performance mapping and use the high performance mapping's energy and performance as the labels for prediction. And yeah, that's the last questions for Professor again. Yeah, that's.
I think there's another questions.
Oh, there's one from Yin, right? And the question is it possible to borrow some ideas from machine learning for machine learning compilation, such as for the search for the optimal tensor program? Do you want to elaborate a little bit on the machine learning compilation part? Like, I guess. So, I think if I understand correctly, sir, is it a question regarding COSA? So I think COSA, it's a good way to formulate for like a tensor algorithms. So in fact, I think the traffic term of each tensor on different buffer can be directly formulated. That's what we know in the quadratic programming. But then the real question there is that the reason why we need to bring in the machine learning is that we really sometimes don't know all the hardware behaviors. So the hardware behavior cannot be captured statically with a mathematical equation directly a lot of times, because like there's frequency scaling, there's basically dynamic schedulers in the GPU, for example, there's L2 that's basically hardware managed. So there are a lot of components that make it a little bit hard on directly just apply static scheduling kind of technique like COSA. So you always need to be augmented with some other techniques. And so if it's a question regarding VAE, I think the answer is yes, possibly we can do that, yes. But again, the data is the key, right? You kind of need to gather more data in order to borrow the VAE idea and kind of use it for the tensor algorithm or tensor program search, yeah.
I think that 2 more questions there.
Yeah, thanks for the other questions. Oh, it's just exciting. So for you, I think the question is, in COSA, considering the tiling approach, is there a scenario where duplicated data assets is required across different tiles? How does COSA address this challenge? So data assets across different tiles. Duplicate assets across different. So if I understand correctly, does that mean that we need to have I think. Do you mean that there is some spatial access to the same data, or is it at the same time? Or I guess I kind of need some clarification on this question. Do you want to chime in, or?
Maybe you can unmute, or you may need to further clarify your questions.
Right.
Maybe we can first move to another question from the brain.
So I can get back to you. Yeah. So the second question is, how do you handle multi-objective optimizations involving memory access, compute energy, and if some of these objectives are dependent on another? So let me see. So I assume this is regarding the for COSA, I will answer it for COSA first. So I think, as you mentioned, that the memory access, compute, and energy are kind of interrelated to each other. So I think compute is kind of very straightforward. You always just want to maximize its utilization so that you can finish this workload fast. So this is more like try to pushing for the compute bound performance. And for the memory access, you were just trying to minimize the traffic objective to reduce the memory bandwidth requirements, right? And the energy is really also a objective of the memory traffic, I would say, because the number of compute is always almost fixed in an algorithm, right? So how to minimizing the data movement across different levels in this case really is the key to minimizing the energy. And for Visa, the question is, can we handle multiple objectives? The answer is yes, if you have that in your training data, right? So but that's a really good question. Yeah. And then in our Genesis, what we're trying to answer is basically how do we achieve this minimum backing store access at different memory hierarchy. But it doesn't really provide you with like an energy model yet. Yeah.
I think you have some additional clarification of his question.
So in tile matrix multiplication, there might be duplicated data access and how the COSA counts the duplicated data access. So yes, it will count the duplicated data access. So I think it's also formulated into the traffic term, if I understand correctly. Basically, as I mentioned before, right? So if you think about the duplicated data access, it is coming from the fact that if, let's say, outside of this buffered tensor, we're doing the loop iteration. So basically, it's with respect to the data flow itself, right? So if we're doing wait stationary data flow, what it means is that we are always loading we are always loading reloading the input and the output regardless in the outer loop, right? So even if we're seeing a irrelevant dimension, so assuming we're doing our wait stationary data flow, meaning that we will have first we'll have a rank that's irrelevant to the weight in the innermost loop, right? So that will be, for example, that will be the P dimension, which is the output, or you can think of it as the M dimension, which is the input output width and height that's irrelevant to the weight in the innermost loop, right? And in that case, you're seeing a wait stationary data flow, but then what it means is that if we're running input and the outputs tiles in the same kind of loop ordering, what will happen is that because we are having P and Q in the innermost loop, so regardless of what you have in the outer loop, even you have let's say for the input, if you have a K dimension, which is output channel dimension that's irrelevant to your input tensor, regardless of whether it's relevant now, right? Because you're loading the P and Q in the innermost loop, you will always need to reload your your input and the output, even you have a basically irrelevant rank, which is the K in the outer loop, right? But so that's kind of like a way we counted this duplicated data assets in our objective formulation, if that makes sense. So it should count. So the data traffic objective should count this duplicated data assets in a tensor algorithm. Hope that answers your question. Oh, so Brian has.
Yeah. Go ahead. Yeah.
So Brian has this question on are the objectives optimized in stages, or are they somehow iteratively optimized together? So in code studies, optimizations are done in one shot. So what we did is we weighted these objectives with different constants, and we just feed them directly into GrowB, which can solve quadratic program very effectively and very efficiently. So we directly can generate a high performance program with one shot objectives. But this is a really good question. So sometimes we could also do some of like iterative solving. So basically, you can say that I want to first optimize for certain things, and then you kind of feed in the constraints, and then once you but then on certain times you probably don't want it to. So basically, you want to specify different constraints. They're good constraints, and then you can also just iterative. You don't have to iterative solve them. You can just solve them in parallel and see which type of constraint give you the best performance. That's another feasible way to do it. Yeah, but current formulation doesn't require it to be optimized iteratively. And I want to mention that weighting them is definitely a challenging though. So what I observe is that I think the utilization objective is actually a so after I published the paper, I think that one is actually not so critical to the performance, because if you think about it, the compute bound objective it's relevant to the parallelization, utilization, that kind of things that directly affects the compute performance. Like compute bound throughput will be affected by the compute objectives, and the bandwidth memory traffic objective will directly kind of solve this memory traffic kind of optimization. So in that case, I think the utilization objective is just a similar objective that's less accurate than the traffic objective. So it's just a heuristic that we had, thinking that maybe if you have better buffer utilization, you should have better traffic. But in reality, that's not always the case, right? So sometimes we probably don't want it to add the utilization objective. Yeah, that's one takeaways I learned afterwards. And but another interesting part is if you want to try to optimize for latent, so for energy, then you might need to also do some iterative solving at different memory level stages, because you really wanted to encourage more traffic to the innermost buffers. And what we didn't solve in the COSA paper is that we didn't do multi-level of memory backing store solving. We basically are only focusing on the DRAM to global buffer and global buffer to the NOC, but nothing within this PE memory hierarchy. But in order to solve for the best energy, you kind of need to probably do some multi-level solving, probably with iterative solvers. Yeah. Yeah, so that's all I have for this question.
Any other questions from the audience? Okay, so today we have very warm Q&A discussion. Actually, I don't have chance to ask questions yet. Yeah, so to be short, I just want to ask two questions. First is regarding your VAE work. So we know that the generative kind of the model, like the VAE or the GAN or like the diffusion. Actually, so actually we want to compress, as your slide shows that we want to compress the raw space to the latent space. So I was wondering, so in that case, whether we have some kind of the potential, like the compression or reconstruction error will kind of limit our design space exploration. Whether we can maybe miss some kind of important design points? So that's my first question. And my second question that, so we know that like your work and other some like those works that the design space explorations actually, so I observed that, so typically, so the design of the schedule, like one schedule that is kind of will be optimized and to operate it to one specific workload, right? Like the ResNet 50 or the GPT-2 or something like that. So I was wondering, because you also work in the industry, I was wondering that because in practice, when we want to design architecture, we want to that to just support it the multiple workloads, right?
Yes.
And especially at the edge side, right? So in that case, so I was curious about the generality of such kind of right now our design paradigm for those design specifications. So from the perspective of the industry, very based on your observation, whether that is already kind of general enough that when we want to fix our architecture after using such kind of design specification. That's my two questions.
Okay, they're really great questions there. Thanks, Professor Yan. Yeah, so the first question is whether there will be, so whether the reconstruction error will affect the exploration space, basically the quality of results of the searched solutions, and basically limit its space. And I think the answer is, I would say it's yes. So basically what I think in this approach is that if we're providing them enough data, so basically it's again this general ML kind of trade-off for the basically the general like trade-off in the ML space, right? So if you don't have enough data, it's likely this latent space, even if it has zero reconstruction error, it might not be sufficient for design space exploration, because every time we're seeing a new algorithm, it hasn't been seen in this previous basically training data, then it's likely that it's possible that we're not able to provide a very accurate estimation of its performance and latency, and we call this out of distribution data, right? So if we're always we're always having these out of distribution data, it's very likely that we will be missing some very good design points. So I think my view to that is you always need to solve this with more data, and that has been shown, and the generalizability kind of has been proven with the large language model, right? It's really how scalable your network is, how much data you can feed to your network, and that will kind of make it either generalizable or not. So that's my first answer. And if you don't have the enough data, so that's our current situation, because we cannot cover all the design points with all our existing data. The question would just be more on this. It's also similar to the large language model trend, right? You kind of need to do reinforcement learning or whatever data collection. You kind of need to still do like a data exploration and exploitation kind of process. You kind of need to have your agent. So the nice thing about like for example RL is that like this RL like exploration algorithm is that now you kind of build your ML algorithm with better prior. So when you do the sampling, hopefully it can help you reach the better performance point in its exploration. And I would say in Visa, we also kind of need to augment it to kind of in the pipeline, saying that like if we're seeing a new algorithm, new hardware design, we will need to have maybe some outer loop to perform this exploration to add to our training data points, and then we can kind of trying to train it with this new data and trying to train a better latent space with this data and trying to further generalize. But we don't know the saturating points yet. Like how much data do we need? That's a harder question to answer. Yeah, but that's a really good question. And the second questions regarding whether in the industry, the design space exploration is generalizable, or is it too specific to one workload? And the answer is also, I would say, design space exploration, so it will be more specific, I would say, to let's say FPGA accelerator. So I think if you can change your hardware, then this is definitely applicable. But then, yeah, but then if your hardware is fixed, let's say, then it requires you to design a more generalizable things. So one methodology to tackle this would be, let's say, you just group multiple of workload to do this design space exploration, which would just make this search more expensive. But that's the one thing definitely people could do, right? So if they want to do it, they could do. But that's not the practice. And from my experience, it's not the practice of how the industry works, right? So that's why we kind of trying to develop our last work, because in reality, people really just look at the speed and fee analysis and based on heuristic, right? Because the space is too huge. And then normally like if a new algorithm comes up, I think in the industry, people need to kind of react really fast. They cannot afford a really long exploration time to further optimize for certain decisions. So if they're making an okay decision, they're okay, basically. So they just need to understand like how much, what is the okay decision. So that's why the last work actually will probably become more practical in the industry, right? So given an algorithm, you can kind of roughly estimate how much buffer size it needs in order to fully exploit the data reuse, right? And in that case, it just directly help you kind of provision for the buffer size. You can just use, and you can kind of trade off different, you can trade off different algorithms needs easily with this curve, right? So that's one thing I think would be helpful for the industry. But I think if we can make the design space loop much faster, then it's also possible that the industry can adopt that. But there's always another level of complexity there. I think mostly it's because, as I mentioned, for the Orgenesis work, is that it takes a very long time to develop a simulator. Right. So if you don't have the simulator, you cannot easily add the features, then and if the evaluation is too long, then in order to do the full circle, for full cycle like design space exploration is very expensive and very time consuming. So that's why it's a mix of multiple things that we kind of need to improve. And in addition to that, I think there's another obstacle is that if we have a new algorithm, let's say we have Mamba now, it's likely that like we don't really have a good understanding to map this algorithm to which simulator can simulate it and which hardware feature can exploit it, right? So there's a lot of like still like human decision to make in order to enable this space search. And we kind of think that it's very important to automate all these processes in order to really achieve like a true automatic design space exploration in that case. Yeah. So yeah, I think that the answer is like twofold, right? It's possible, but it requires way more work. And then the second one is that there are some like speeds and fees analysis we could do to kind of help the designers make decisions. Yeah, that's
Okay, thank you. Thank you very much for your insightful answer. So if there's no more other questions, let's thank our speaker again. So today we really have very, very warm discussions and we really learn a lot from your excellent work. Okay, thank you, Jenny. Yeah, and also thank everyone to attend our this week's seminar talk and see you next time. Thank you, Jenny. Thank you. Have a wonderful day.
All right, have a good day.
Bye.